The project background: the problem is rising the municipal waste combined with low recycling rates poses a serious threat to the environment, while manual waste sorting remains low, inefficient, and highly prone to the human error. So for the solution, AI integration utilize the image recognition to automate the material detection, while accessible the technology such as teachable machine enables the rapid and efficient model development. So for the project goal, the objective is to develop an AI model that accurately sorts garbage to enhance the recycling efficiency and reduce landfill impact.
Our three main objectives is to collect data, train model, and evaluate accuracy. For collect data, we gather diverse image datasets for paper, plastic, and tin or aluminium. For train model, we develop a classification model using teachable machine. And lastly, to evaluate accuracy, we test the model's ability to correctly identify waste categories. So we have three scopes. The first one is paper waste, and then we have plastic waste or tin or aluminium waste. So for paper waste, we have such as newspaper, cardboard, and office paper. For plastic waste, for example, like bottles, wrappers, or container, and for tin or aluminium waste, such as soda cans or food tins.
The framework of AI-based waste classification system included the input layer, backend, and the output layer. The input layer, the data acquisition process begins by capturing the live video frames of the waste materials, such as the paper, plastic, and the tin, using a webcam. So this webcam acts as the primary input device that observes the physical waste item placed in front of it. Through the user interaction, the system serves as a bridge between the physical object and the digital machine learning, allowing the user to present the waste items to the camera of recognition. So the capture video stream is then converted into a raw digital image frame, which are processed by the machine learning model for the features extraction and the classification. So for the back end, once the image is captured, the system performs the image streaming to transmit the visual data in real time into the processing cores. The incoming data undergoes a three-stage processing pipeline. First, data pre-processing is applied to resize the image and convert them into numerical tensors suitable for the machine learning input. Next, the features extraction stage uses the MobileNet architecture to analyze the important visual characteristics such as the texture, shape, and the material age. So finally, the classification engine processes the extracted features and computes the most probable materials category using a predictive model. For the output layer, after the classification process is completed, the system performs the result rendering by translating the complex AI probability values into a simple and user-friendly visual formats. So these results are presented through an intelligent dashboard that display the final waste material classification along with real-time confidence bar. So based on the confidence level, the system also provides user guidance by giving the instant feedback such as the adjusting the lining condition or repositioning the object. So to help them maintain a high confidence threshold and improve classification accuracy.
For methodology part, we have three phases, which is the first one is data acquisition and pre-processing, second is model development, and third is the system flow. For the first one, waste images are captured using a webcam and organized into three categories, which is paper, plastic and tin, or aluminium. Approximately 100 to 150 images were collected for each category. To improve the robustness of the model, images were captured under different lighting conditions, angles, and also distances. This helped the model learn generalized visual features rather than memorizing specific objects. Next is model development. The classification model was developed using Google Teachable Machine, which applies a supervised learning approach. Transfer learning was used with the MobileNet architecture to extract meaningful visual features. These features including texture, shape, and surface reflexivity, which allow the model to distinguish between different types of waste materials. The final phase is the system workflow. During this operation, live images are captured through the webcam and undergo basic preprocessing such as resizing and normalization. The processed image is then passed into the trained classification model. The model generates probability score for each waste category, and the category with the highest confidence score is selected as the final prediction. The result is displayed on the dashboard in the real time together with the confidence score.
For our dashboard design, the purpose is for primary interface connecting the user and the AI model. Our goal is to provide an intuitive real-time feedback loop for waste classification. So as you can see, the left side it displays the live video streams, which is the eye of the system, and it also allows user to adjust positioning and lighting. And on the output panel, the right side, it has a list target categories. Like for our system, we have paper, plastic, tin or aluminium, and they have a confidence bars which fill from 0 to 100% to show a certainty, and then the real-time color changes indicate positive matches.
The results and discussion. This chapter presents the finding obtained from the development and testing of the AI-based waste classification system. The results are divided into two sections, that is, the internal performance metrics generated during the model's training phase using Google Teachable Machine, and the external performance results obtained through manual testing with unseen waste items. Internal performance metrics. The explanation is breakdown to four important parts. The first part is data set overview. Training conducted on three distinct classes that are plastic, paper, and tin or aluminium. Internal validation confirms that highly successful learning phase. Accuracy metrics. Achieved 100% training accuracy, reached maximum accuracy immediately after the first epoch. Maintained stability throughout the 50 epoch cycle. Third is loss function analysis. Error rate dropped rapidly to near zero, that is lower than 0.01. The flag curve indicates the model perfectly memorized the training features without significant error. Lastly, confusion metric performance. Zero misclassifications. There are 0 false positives and 0 false negatives. Perfect identification across all validation samples. There are plastic waste is 45 to 45, paper waste is 65 to 65, and tin or aluminium is 44 to 44. Now on to external performance results. First is testing methodology. Conducted manual testing using 13 new waste items to evaluate real-world robustness. Items selected were strictly unseen data, not included in the training dataset. Next is overall performance. achieved a success rate of 7 out of 13 correctly identified items, that is 54% of accuracy. Results highlight a significant gap between training performance, that is 100%, and real-world application. The last is category-specific insights. Paper waste demonstrated high reliability with minimal errors. For plastic and tin aluminum, showed significant misclassification rates, primarily due to visual similarities in texture and reflection. Now on to the part of discussion. First analysis that was done during the discussion is performance discrepancy. Significant gap observed between training accuracy, that is 100%, and real-world testing accuracy, that is 53.8%, indicates overfitting. The model memorized specific backgrounds or lighting details instead of generalized materials features, resulted in poor generalization when presented with unseen items. Next is visual misclassification. Texture similar that happened between paper and plastic. Crumpled tissue paper misclassified as plastic, and the cause is the model struggled to distinguish soft fibrous paper texture from crumpled plastic bags. Next is label interference. Deodorant cans and food packaging misclassified as paper. The cause is the model prioritized text and paper labels over the object's actual shape or material. The last is reflection issues that happen between plastic and metal. Plastic bottles or container misclassified as tin or aluminum. The cause is the model interpreted the reflective shine of the transparent plastic as metallic properties. Now on to the category performance. The best performing category was paper waste, that got 80% of accuracy. Successfully identified distinct items like newspapers, boxes, and receipts. The insight is the text-heavy and matte-textured objects are easiest for the model to distinguish. The worst performing category was tin or aluminum with 33% of accuracy. High error rate with items like carbonated drinks misclassified as plastic. The insight was lighting conditions significantly impacted the detection of metallic texture. The last part in the discussion is constraints and limitations. First is lighting sensitivity. The model relies heavily on specific lighting conditions rather than intrinsic object features. The evidence is misclassification of items like carbonated drinks indicates a failure to detect metallic reflection under variable lighting. Second is lack of dataset diversity. While the dataset yielded perfect internal validation result, it lacked the variety needed for the real world. The model failed to learn subtle visual differences between materials with similar textures, specifically shiny plastic versus metal. Vulnerability to background noise. The model struggles to segment objects effectively from complex backgrounds. Prediction errors are increased significantly when the items were presented in a new environment distinct from the clean, controlled training data. So now, conclusion. This project successfully met its objective of developing a functional AI-based classification system using Google Teachable Machine. Although the model achieved perfect 100% of accuracy during the training phase, real-world manual testing revealed an overall accuracy of 53.8% due to overfitting and sensitivity to environmental factors like lighting. Ultimately, the study stands as a successful proof of concept, demonstrating the feasibility of using low-code AI tools for environmental solutions while highlighting that future iterations require significantly more diverse datasets to ensure reliability in complex real-world conditions.